I guess we'll go ahead and start. This is the direct instruction for March 28th. And these will be our topics we'll go over. Now the first one is solving using the square root property. Square root property says if you got something squared equal to something else, then you can drop the squared and you put a plus or minus square root on the other side. Now it really is as vague as what I just said. This can be anything. As long as you have something squared is equal to something else, and you can apply this. Now the part that's squared has to be by itself on the side. Can't have anything in front of it, can't have anything after it. If I looked at a simple example where we got x squared is equal to 5, well, we have the entire left side squared equal to something else. So square root property says we drop our squared and we put a plus or minus square root on the other side. And that would be our answer. Now you don't have to have just a single letter. You can have anything squared. This would be the right form. We have something squared equal to something else. So we'll drop our squared. And we'll put a plus or minus square root on the other side. Now at this point, I can solve this. Take the negative 2 over, and we get x is equal to 2 plus or minus square root of 3. Now one of the problems that I noticed is where you had to get the part that's squared by itself. And this would be an example of that. You can only take the square root property if the entire side is squared. So on this one, I'm first going to have to move the negative 1 over. So we got 2 times 4x minus 1 squared is equal to 5 plus 1. That's the same as adding 1 to both sides. 5 plus 1, 6. Now the squared part is still not by itself because we've got a 2 in front of it. You always do the opposite operation. Here is a minus subtraction, so we added. So that's why it's a plus 1. And here, this is multiplication, 2 times this. So we'll divide. So 2 times 4x minus 1 squared over 2 is equal to 6 divided by 2. Those 2's would cancel. Then I got 4x minus 1 squared is equal to positive 3. And now, this is in the right form. It just simply says if you got something squared equal to something else, then you drop the squared, and you put a plus or minus square root around the other side. Take negative 1 over, and we get 1 plus or minus square root of 3. And then we divide both sides by 4. And we get 1 plus or minus square root of 3 over 4. Those 4's would cancel. So that would be our answer. Now once we look at the quadratic formula, I'll talk more about some simplifying techniques once you get down to this point. But that was the square root property. Now the next one is solving using the zero factor property. Let me clear this off. Zero factor property says if you got something times something else is equal to 0, then you can set each factor equal to 0. Now the idea behind these techniques we're looking at here first is that you're working with a quadratic, but you don't have to. This would apply if you're in trig. The square root property would apply if you're in trig also. So it really is as vague as what I'm just saying. But if you got something times something else equal to 0, then you just set each factor equal to 0. And from there you'll be able to solve it down. Okay, let's take a look at this one. Now I like this name the best. Different books have different names for it. But this one tells you exactly what to do. So the title is your steps. 0. That says get 0 on one side, which we do. Then factor says to factor the other side. Well, this factor is using the PSD. Well, factor is x minus 2 times x minus 7. So now we got 0 on one side. We've factored the other side. We're going to set each factor equal to 0. So I'll set x minus 2 equal to 0, and I'll set x minus 7 equal to 0. And that gives us x equals 2 and x equals 7. So those would be our two answers. Now if I had started out with something looked a little bit different, let me double check that. Yeah, that'll factor. Okay, first off on this one, I notice a zero factor property. It doesn't have a 0 on one side. So we're going to take this negative 50 and move it over. So we got x squared minus 15x plus 50 is equal to 0. So again, have to get 0 on one side first. And then this factors using the PSD. So factors as x minus 5 times x minus 10 equals 0. Now the zero factor property says you get 0 on one side, you factor the other side, you set each factor equal to 0. So we got x minus 5 is equal to 0, and x minus 10 is equal to 0, which gives us x equals 5 and x equal to 10. Now don't assume that factor means you have to use one of the factoring techniques we've seen. Factor means to write as a product. So if you had a problem that looked like this would still apply because we got something times something else equal to 0. Then you'd set each factor equal to 0. And I won't continue it, but there's none that hard in the material. But zero factor property is much more than just working with quadratics. Just as long as you can write anything as a product, you can use this principle. Now the next topic is finding a quadratic given zeros. And we have to look at some notation, some definitions before we understand this. If I was solving x squared minus 5x plus 6 equal to 0, then I would factor these. And once I did that, these are called factors. Then you set each factor equal to 0. and you solve them. And these are our answers. But they also got another name. They're called zeros, and they're even called roots. Well, what they're wanting you to do with this next topic is to go backwards. So you want to start off with your answers, and then you want to go back up to get your original quadratic. For example, if I start off with x equals -1 and x is equal to 1/2. Now, to go backwards, go from here to here, it looks like I'd take the 2 and move it on the same side as the x. Here I'd move the 3 on the same side as the x. So that's what we'll do here. I'll move the -1 on the same side as the x, and I'll move the 1/2 on the same side as the x. So we got x plus 1 is equal to 0, and we got x minus 1/2 is equal to 0. Now, one thing that you can't see in this is we don't want fractions. So on this one on the right side, I can multiply everything by 2 to get rid of the fraction. When I say multiply by 2, multiply by the LCM of all our denominators. We only have one denominator, so that's our LCM. So I'll take 2 times x minus 2 times 1/2 equals 2 times 0. And so I'd give us 2x minus 1 equals 0. Okay, now going from this step back up to this step, it looks like I put parentheses around each factor and put them next to each other. So it'd have x plus 1 times 2x minus 1 is equal to 0. They don't really care about the equal 0 part, they just want the left side, but it doesn't hurt to put it there. And then going back from this step back to this step. We got x times 2x, which is 2x squared. We got x times -1, which is -1x or negative x. 1 times 2x, which is 2x, and 1 times -1, which is -1, which would give us 2x squared plus x minus 1 equal to 0. And like I said, all they're wanting is this piece right here. And that's going backwards. That's where you're starting again with a 0, and then you're coming up with the original quadratic. Now, the next topic is kind of a tricky one. I'm going to write the steps down for it. Solving using completing a square. Like something. Step 1. Divide everything, all the terms, by the number in front of the x squared. Now I'm going to give you all these steps, but you shouldn't run across items that we need to use every one of these. Okay, step 2. Take the number, the constant term, to the right side. Step 3. Take the number before the x, coefficient, multiply it by 1/2, square it, and then add to both sides. Step 4, factor the left side. And step 5, use the square root property to solve for x. This is a process when I took college algebra many years ago I didn't understand. And first semester teaching some 20-some years ago, I really did a poor job at explaining this because I didn't fully understand it myself. Well, you only embarrass yourself that much in one class period. At that point, you come up with a step-by-step. And if you follow these steps, then it's not too bad. Let me clear this off, and I'll make up an example. We'll start off with an easy one first, and then we'll look at a harder one. Let's see, x squared minus 8x plus 1 equal to 0. Now this will not factor. If I tried to factor this using the PSD, thinking I'd use the zero factor property, it doesn't work out well. The square root property wouldn't work out well because we have the middle term. So completing the square is a method, although we'll see there's an easier one after this. Step 1, divide everything by the number in front of the x squared. There is no number in front of x squared. Step 2, take the number of the constant term to the right side. So we got x squared minus 8x, and I'll take the 1 over to the right side and it becomes a negative 1. Step 3, take the number before the x. Number in front of our x is a negative 8. You do this over on the side. Take the number before the x, multiply by half, square it, and then add to both sides. It's always times a half, and it's always squared. The only thing that changes is whatever number's in front of your x. So that gives us negative 8 times a half is negative 4 squared, and negative 4 squared gives us positive 16. And that says then add to both sides. So I got x squared minus 8x plus 16 is equal to negative 1 plus 16. So that's x squared minus 8x plus 16 is equal to negative 1 plus 16 is 15. Step 4, back to the left side. This factors as x minus 4 squared. Now I'm not some kind of genius in factoring. There's a trick to this. Whatever number's inside of parentheses right before you square it, sign included, is always what goes right here. So there really is no factoring involved. That'll come in handy in the harder type, which I'll look at next. Step 5, use the square root property to solve for x. We now have something squared equal to something else, so I drop the squared, and I'll put a plus or minus square root around the other side. Now square root of 15 doesn't simplify because 15 is 3 times 5. So to solve for x, I take negative 4 over, and we got x is equal to 4 plus or minus square root of 15. And that's our answer. Now that's the easiest type. Doesn't mean it's an easy process, but it's the easier of all of them because there's an even number before the x. We're going to look at where we have an odd number before the x and see what happens. And when I make these up, it doesn't matter what numbers I put there. I just make sure that there's an odd number. Like, let's put a 7. Okay. First step. Divide everything by the number in front of the x squared. There's no number in front of our x squared. Step 2. Take the number of the constant term to the right side. So I'll take the negative 2 and move it over. So we got x squared plus 7x is equal to 2. Step 3, take the number before the x, multiply by half, square it, then add to both sides. Well, the number that's in front of our x this time is a 7, so we're going to multiply it times a half, and we'll square it. Now, you always want to leave this as fraction. Do not change it to decimal, Change it to decimal, sometimes you get the correct answer, sometimes you don't. So if you leave it in this form, it works out best. 7 times a half is 7 halves, and 7 halves squared gives us 49 over 4. 7 squared is 49, 2 squared is 4. And then we want to add that to both sides. Now what happens when you have an odd number before your x is you always have a fraction appear in your problem. Okay, well this is x squared plus 7x plus 49 over 4. Now this right here is a mixed number form. So we can take 2 times 4, which gives us 8, plus 49 gives us 57 over 4. Again, I took the number out in front, multiplied times the denominator, and added the number on top. Step 4, factor the left side. This would be kind of hard for me to factor if I didn't remember the trick. So this factors as x plus 7 halves squared. Again, whatever number's right here, right for your squared, sign included, is always what comes down at this point. And then step 5, use the square root property to solve for x. We now have something squared equals something else, so I drop my squared. And I'll put a plus or minus square root around the other side. Now we talked about, I think it was in the last unit, maybe it was 2 units ago, but we talked about fractions and radicals. And we said 2 items have to be true. You can't have a fraction inside of a radical. Well, that's easy. We got a property says if you got a fraction inside a radical, you can split it up. You can put a radical around top, radical around the bottom. But square root of 4 is equal to 2, so that simplifies. But that created another problem. We can't have a radical in the denominator. I shouldn't have to do this, but I'm not seeing it. It's definitely divisible by 3. Let's see, 127. Okay, that doesn't break down any. Now we're going to take the 7 halves and move it over. It becomes a negative 7 halves. I'm going to talk about this again with the quadratic formula, but one of the simplified form says that if you got, for a simplified form, if you have 2 fractions like this, you want to merge them together into a single fraction. So we've got negative 7 plus or minus square root of 57 over 2. Not all books stick to that principle, but typically simplified form means a single fraction. And that's completing the square. Now let's take a look at solving using the quadratic formula. And then we'll talk about the different simplified forms. Usually I always show one example of the quadratic formula, but then I'll talk about all the different simplifying techniques, because that's usually the challenging part. Now quadratic formula says if you got something of the form ax squared plus bx plus c is equal to 0, typically a, b, and c are numbers. Then your answer will you can get from this formula. X is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. Yeah, I don't remember exactly what I used before. I think I had a 7 there, but Let's take a look at this problem. Now remember, with completing a square, this would be hideous, because we've got an odd number before our x, and we'd have fractions appear in the problem. We'll still have fractions, but we're going to see it's not as hideous as it was before. Now with the quadratic formula, you have to identify your a, b, and c. A is whatever number is in front of your x squared. Well, there is no number in front of our x squared, so it's the invisible 1. B is whatever number is in front of our x, which is negative 7. And c is our constant term, a number at the end, which is 2. Now I always tell people, if they mess up on signs, it's a good idea to go through and put parentheses in everywhere you have a variable before you plug in your numbers. So we're going to have negative b plus or minus square root of b squared minus 4 times a times c all over 2a. Now I notice how everything else remained exactly the same. The negative, plus or minus, square root, second power, minus 4, the 2. Only thing I did is replace all the a's, the a, b's, and c's with parentheses. Now we said b was negative 7, so everywhere I have b, I'll put in negative 7. We said a was 1, so everywhere I have an a, I'll put in a 1. And we said c was 2, so everywhere I have a c, I'll put in a 2. Now negative negative gives us a positive 7, plus or minus. Negative 7 squared is 49, minus 4 times 1 times 2 is 8, over 2, which then gives us 7 plus or minus square root. 49 minus 8 is 41, all over 2. And that would be our answer. Now, typically, if you can use square root property, then you do. If you can get the part squared by itself, and then a number on the other side. If it'll factor, you can use zero factor property. And then if you have a quadratic and will not factor, you can't use square root property. Typically, if you're given a choice, you want to use quadratic formula because it's much simpler. You can get the same answer with completing a square, but it's just lengthy. It gets kind of tedious. Now let's talk about simplified form. And this applies to the quadratic formula. It also applies to completing a square. It applies the square root property. And it actually applies in a few other places too. Now the first one we saw with an example. Simplified form typically means a single fraction. Now there's going to be some exceptions to that we'll talk about though. If I'm working the quadratic formula, and I've worked the problem down, and we have an I up here. Now remember how you get an I is you have a negative number inside of your square root. That negative comes out of the square root as an I. So if you have an I in the problem, then split the real part separate from the imaginary part. That's standard form. Standard form says you have to have your real part separate from the imaginary part. Which means over here, even though we said simplified form typically means a single fraction, in this case we're going to split this up. We'll put the 3 over 7 plus or minus square root of 7 over 7 with an I to the side. And that would be our answer. And that's if you have an I appear in the problem. If the square root disappears, then split the problem into a plus version and a minus version. So if the square root disappears. Well, what I mean by that is you're working a problem down. Those indicate steps you can't see. And we come up with this. The square root has disappeared completely. Well, at this point, what that plus or minus means is you're going to have 3 plus 2 over 5, and you'll have 3 minus 2 over 5, which then gives us 5 over 5, or 1, and 3 minus 2 is 1, so we'll have 1 over 5. And those will be our two answers. So again, we do not want to leave it as a single fraction in that case if the square root disappears. And then there's one last one. It says use the 3-number rule if possible. 3-number rule appears a lot when you're using the quadratic formula, though it can appear other times. What that looks like is if I'm working a problem down and I get it down to this point here, I got 6 plus or minus 9 square root of 5 over 12. If you can divide this number, and this number by the same number, do so. Well, those are all divisible by 3. 6 divided by 3 is 2, plus or minus. 9 divided by 3 is 3, square root of 5. And 12 divided by 3 is 4. And that would be our answer. Now you have to be careful that it is the 3 numbers. A lot of people, when they're using the quadratic formula, will run across a problem that looks like this. And they'll think that they can simplify it. That you got a 5 here and 10 here, and you can divide those. And you can't. Because it has to be these 3 numbers. Now some books, some instructors will teach us as the triangle rule is what they call it. If you can draw a triangle between those numbers, then you can, and they're all divisible by the same number, then you do so. So again, this is, there's no simplification you can do here. This would just be your answer. You know, if I went through my methods, simplified form typically means single fraction, okay? If you have an I, we don't have an I. If the square root disappears, square root did not disappear. And we just said we can't use the 3-number rule here, so this is simplified as it gets. Now those, like I say, those simplified forms I just talked about apply to not just only the quadratic formula, but completeness square and square root property. Now let's take a look at solving log equations with a single log. And actually, I may have these in the wrong form. So let me move this one. There we go. Converting from log form to exponential form. And let me move this one too. Yeah, that'll work. Now, when I was coming up with the topics to cover, I mainly just went through the material and looked at what was presented first. So it's a little bit out of order in the material, but this is the way it should be covered. So let me clear this off. You can read in the book about where logs are used at. They'll give you application problems. I'm not very good at coming up with application problems. One big use of logs, though, is they use it in the Richter scale for earthquakes. It's also used as an invaluable technique in calculus. Helps you do some simplifications so you can apply other properties, other formulas. Now our log form looks like this. We got log And then got a b here. This is typically a number that's smaller that's set down of q is equal to p. How you read that? That's log base b of q is equal to p. Now that's our log form. This exp stands for exponential form. We would rewrite that if it was in this form as b to the p is equal to q. Now all of these have names. The only one that's really important is that b. It's referred to as your base. Now some of the problems that you'll have to work, they'll ask you to switch back and forth between the different forms. So we're going to start off with this form right here. And we want to write this in exponential form. Well, how you do this is you match it up against your form up here. We said the number that follows your log that's a little smaller and set down is going to be your b. So the 3 is our b. We then said whatever follows that is your q. So this will be our q. And then the other side of the equals will be our p. And our exponential form is b to the p is equal to q. So we just plug in what we identified. B was 3, P was 2, and Q is X. And that's our answer. Now they're not necessarily looking for you to do any kind of simplification there. We're just practicing going back and forth between the different forms. Now let's look at one more. And then we'll look at a problem going the other direction. Okay, we have this right here. Same instruction. We want to write in exponential form. Well, if I match it up against my log form, the number that follows your log that's smaller is set down is going to be your b. So this will be b. And then what follows that is your q. And then the other side of the equals is your p. And our exponential form is b to the p is equal to q. So we'll now plug in our b, p, and q. So we got 5 for the b, p was 7, and q was x plus 1. And you can probably see where we're going to head with solving log equations. You'll use this technique to rewrite it in this form, and then you'll solve for x. But we'll get to that here shortly. Let me clear those off. Let's say I start with 2 to the 4th is equal to x. We start off in log form, and then we want to write it, or exponential form, and then we want to write it in log form. Well, if I match it up against my exponential form, my exponent, my power is p, so the 4 is going to be the p. What's immediately left of it is b, so the 2 is b. And then the other side of the equals is your q. Now our log form is log base b of q is equal to p. So I just plug in what is identified. B we said was 2. Q we said was x. And p is 4. And that would be our answer. Now that was converting from log form to exponential form and vice versa. Another item you didn't know is how to simplify log expressions without a calculator. So let me clear this off. And I'm going to work a couple examples, then I'll write a property down. It's a very simple idea, but the property makes it look complex. We got log base 5 of 25. Well, our base is 5. So what we try to do is we try to rewrite this number here, the 25, as our base to a power. And 25 I can rewrite as 5 squared. Now if you can get these two numbers matching, they're both 5s, then the log and those two numbers are going to cancel, and the exponent drops out of the exponent, and that's our answer. So our answer is 2. Actually, let me show 3 of these. Let's look at this one. Log base 3 of 81. So again, our base is 3. I'm going to try to rewrite the 81 as 3 to a power. And that'd be 3 to the 4th. Again, if you can get these numbers to match, then the log and those numbers are going to cancel. And the exponent drops down out of the power, and that's our answer. Sometimes it's not so easy to identify. Maybe I'll show 4 of these. Keep thinking of ones I'd like to show. For this one here, for example, I got 8. 8's easy. That's 2 to the 3rd. But the property doesn't apply if this is trapped in the denominator. We looked at problems earlier in the course where you can move something opposite of where it's at in a fraction, and the sign of the exponent changes. When I move that 2 to the positive 3 up on top, it becomes 2 to the negative 3. And again, if you get these numbers the same, then log and those two numbers cancel, and your answer is negative 3. One last one. If you got a radical of some sort, then always rewrite the radical in fractional power form. Square root of 9, for example, is 9 to the 1/2. You notice when I do that, 9's match, so log and 9's going to cancel, and our answer is 1/2. Now the property says we got log base b of b to the p power. That's going to equal to p. So again, this says if these numbers match, then log those numbers is going to cancel and just give us p. This morning, actually, I put this formula up, and a bunch of confused looks from students. I don't usually put it up first. And then I worked problems, and then I went back to the property, and they said, oh, okay, that makes sense then how those have to match. So again, a property makes it look kind of complex, but it's a fairly simple idea. Not always the simplest to get it in the right form, but the concept is fairly straightforward. Now, the next thing you need to know how to do is solve log equations with a single log. So let's talk about that. I'm going to give you all the steps for solving a log equation, but there's none that are hard enough where you need all these steps. So solving log equations. First step is to get everything with a log on one side, numbers on the other side. When I say numbers, I'm talking about the constant terms. Step 2, this is the one we won't have to do. We use properties of logs to get a single log. That's not covered in this course, the properties of logs. I mean, besides the properties I'm showing you. Step 3, use the definition of a log to rewrite in exponential form. And then step 4 is solve for x. And step 5 is to check your answers. Actually, let me write semi-check your answers. You cannot have log of 0 or log of a negative number. You don't need to fully check it. You just need to make sure it doesn't cause any of those cases. Okay. Yeah, clear this off. And we got log base 3 of, let's say x, is equal to 2. And we want to solve for x. Step 1, get everything with a log on one side, numbers on the other side. Well, everything with a log is over here, numbers over here. Step 2, use properties of logs to get a single log. We have a single log, and that's the hardest type you'll run across in the material, is where you got a single log like this. Although there may be problems in the textbook where I didn't look on that. But if you do have any questions, you can definitely contact, put a post out in the discussion or email me. Step 3, use definition log to rewrite an exponential form. Well, remember, this is our b, and then what follows that is our q, and the other side is our p. And our exponential form was b to the p is equal to q. B we said was 3, P we said was 2, and Q is X. And that's step 3. Use definition log to rewrite an exponential form. Now step 4 says solve for X. Well, 3 squared is 9, so I get X is equal to 9. But remember, you have to semi-check your answer. So I want to plug this 9 back in, and I just want to make sure I don't have log of 0 or log of negative number. Well, if I put 9 in here, well, that's log of 9. It's not 0, it's not negative, so that's our answer. Now let me show one more. A little bit harder one. I never saw any of this hard, but still exact same idea. Okay, step 1, get everything with a log on one side, numbers on the other side. Well, numbers over here and our logs over here, so that's done. Step 2, use properties of logs to get a single log. Well, we have a single log. We have a log of something. Step 3, use definition log to rewrite an exponential form. Again, whatever number follows your log, the smaller is going to be our b. And then whatever follows that is your q, and then the other side is your p. So our exponential form is b to the p is equal to q. Well, b we said was 2, p is 3, equals q, which is x plus 5. And then step 4 is to solve for x. Well, 2 to the third is 8. Bring the 5 over, and we end up with x is equal to 3. But we have to check it. Make sure that doesn't cause log of 0 or log of negative number. If I put 3 back up here, 3 plus 5 is 8. That's not 0 and it's not negative. So that checks. And that was solving log equations with a single log. Now the next topic is evaluating exponential functions. So let me clear that off. If I have, for example, f of x is equal to 2 to the x plus 3 power, and instructions are asking you to find f of 1. Well, this is no different than before when we evaluated functions. You go through, and everywhere you have an x, you're going to plug in whatever number you have inside of parentheses here. So we're going to have 2 to the 1 plus 3 power. 1 plus 3 is 4, and 2 to the 4th gives us 16. Now another example. If I have something that looks like this, f of x is equal e to the x, and I'm wanting to evaluate, find f of 2. It's still the same idea. You're going to put 2 in for x, and we got e squared. Now e is a number like pi. It's equal to 2.7, a bunch of decimal places. How you get e on your TA3, TA4 calculator, different calculators have different ways of getting this, but all of them should have it in some form, is to get e, you do second button, and then you push the ln button, and that accesses the e above it. And you notice on mine it says e caret beginning parentheses, and then we're putting a 2 in. And then enter. And it gives us, I'll take it 2 decimal places, 7.39. So that's how you evaluate an exponential function. Now if you're wondering what is an exponential function, it's where you got a variable in your exponent. Now we have solving exponential equations, but along with that is this last one. I don't have these in a very good order, it looks like. Let me move that. And let's take a look at solving using equality of exponents first. So solving using equality of exponents. Different books have different names for this. It'd be nice if they had some standards in mathematics, but it says if you got b to the p power is equal b to the q power, then you can set the exponents equal to each other. P is equal to Q. Very simple idea. Sometimes it's not so simple to get in that form, though. That's sometimes the tricky part. And sometimes you can't, which we'll look at we'll look at some examples where you can't and how to solve those. But let's say I have 2 to the x is equal to 8. And this is an exponential equation because it's got a variable in the exponent. Now this says if we can rewrite both of these as the same number to a power, so what you do is you start with your larger number, which is 8, and you try to rewrite it as the other number to a power. Well, 8 is 2 to the third. And equality of exponents says if you can get this number and this number the same, both of them 2 to a power, then it's like you can cross out the 2's and you set the exponents equal to each other. So that'd give us x equals 3. Like I say, a fairly simple idea, but some of them maybe not be so simple to get in the right form. Like, let's take a look at this problem here. 4 to the x minus 2 is equal to 8. If I try to rewrite 8 as 4 to a power, 4 to the first is 4, 4 squared is 16. There's no way I can rewrite this as 4 to a power. So instead, I think both sides. And I see 4 is 2 squared, and 8 is 2 to the third. So sometimes you have to work on both sides in that manner. Now you notice when I rewrite the 4 squared and I put the new exponent up there, there was already an exponent up there. I had to put parentheses around what was already there. Well, now since they're both 2 to a power, the 2 is going to cancel. And we'll have 2 times x minus 2 is equal to 3. So you set the exponents equal to each other. Now I can solve this. 2 times x is 2x. 2 times negative 2 is negative 4 equals 3. Take the negative 4 over and it becomes a positive 4. And that gives us 7. Divide both sides by 2, and we get x is equal to 7/2. And that'd be our answer. Okay, now let's talk about some other forms. And we've seen this in earlier tonight. Remember, if you have radicals, you can rewrite that in fractional power form. This would become 2 to the 1/2 power. So never want radicals when you're working with these. You'll always want to rewrite it, assuming you use an equality of exponents. Now they're both 2 to a power, so those 2's cancel. And we got x is equal to 1/2. Now one more of the same type that we saw earlier. Like if I got 2 of the x is equal to 1 over 8. Well, 8, remember, was 2 to the 3rd. And we did a little trick earlier where if you had 2 to the 3rd in the denominator, you can move it up to the top, to the numerator. And when we did that, the sign of the exponent changes. So it becomes 2 to the negative 3. And again, if these are both 2 to a power, the 2's cancel. And you set the exponents equal to each other. So our answer would be x equals negative 3. So again, a fairly simple idea, but sometimes not so simple to get it in the right form. You may have to do a little manipulation to get it there. Now let me erase those. And let's say we got 3 to the x is equal to 5. Well, if I start with 5, the larger number, there's no way I can rewrite that as 3 to a power. If I look at both sides, well, they're both primes. I'm not going to be able to do anything with this. So it doesn't work. Equality of exponents doesn't always work. So we have solving exponential equations. And step 1 is get the part with the variable and the exponent by itself on one side. Actually, let me go ahead and start this on a new page. Since we're not really going into a lot of depth on log properties, then I need to actually spell everything out here. Okay, what I mean by itself on one side is no numbers in front of it or behind it. Step 2, take natural log of both sides. Now natural log, this is trivia, but natural log is a log with base equal to e. So when you see that ln, that's natural log. It's from the French, log naturel, and that's where you have base is equal to e. Step 3 is using properties of logs, get the variable out of the exponent. And when I say properties of logs here, simply put the exponent in front of ln. And then step 4 is solve for x. And we'll see what I mean by that. It's usually a little wordier than I normally write down for solving exponential equations. Step 1, get the part of the variable and the exponent by itself on one side, no numbers in front of it or behind it. Here we have 3 to the x. There's nothing in front of it, there's nothing after it, we just simply have 3 to the power. So that's done. Step 2, take natural log of both sides. So we can have natural log of 3 to the x is equal to natural log of 5. Now step 3 says using properties of logs, get the variable out of the exponent. And I say simply put the exponent in front of the ln. So in this one, I'm going to take the exponent, the x, and put it out in front of the ln. So we've got x, natural log of 3 is equal to natural log of 5. And that's one of the properties of logs. Properties of log says that if you have log of something to a power, you can take the power and put it out in front of the log. Now step 4 is to solve for x. Now to get x by itself, we're going to divide by what's behind it. So we're going to divide both sides by ln of 3. And those ln of 3's will cancel. And you got x is equal to ln of 5 over ln of 3. Now you cannot cancel the ln's, the natural log, because those actually modify the number. But we can plug that in the calculator. So if I push my ln button right here, I put in 5, and I'll put a closing parentheses divided by ln and then 3 in closing parentheses, and then press enter. 2 decimal places, that would give us 1.46. Now this natural log of 5 over natural log of 3 is the exact answer. This is an approximation. But that's how you can find out what value of x works here. So 3 to the 1.46 power will give you 5. Well, I rounded it, so it probably won't give you exactly 5, but it gives you really close to 5. But that's how you solve an exponential equation, assuming equality of exponents doesn't work. And that was this right here. Now also, some of the problems involved graphing log functions to different bases. If I graph this, for example, y is equal to log x. Notice that there is no base here. There's no number that follows my log the smaller it's set down. When you don't have a number there, by default, it's base 10. That's trivia. You don't need that for graphing purposes. But if I come over here, if I go to graph, if I press y equals, now press clear out what's there, I have a log button. If I push this log button, that's base 10. So I'll put x in, and I'll put a closing parentheses, and then graph. Then that'll give us our graph. So that's not a big deal. What it would look like is these graphs never just stop. It actually got so close to the y-axis it looks like it's one with it. It keeps going down forever like that. If I wanted to graph natural log of x, we already said earlier if you have natural log, that's base e. So your base is going to equal to 2.7 and a bunch of decimal places. Well, still not a big issue. But if I come over here, press y equals, clear, we have an ln button. This is base e. And then I do x, closing parentheses, and graph. Kind of looks similar to the one we just looked at. Again, looks like that. When you have different bases, it affects how close it gets down to the x-axis in this particular graph. Okay, now the real issue, and what we're going to talk about here, is how do you handle it when you have, for example, 3 there, and you're wanting to graph that. 2 different ways. I'm going to first talk about the calculator, and then I'll talk about the by hand method. By hand method's kind of clunky. Okay. Now we got a problem. We got two buttons. We got a log button, which is base 10. We got an ln button, which is base E. We don't have a base 3 button. And there's no way they could have that because you'd have an infinite number of buttons at that point. The newer T84 actually does have a way to put in any base. But what we use is we use something called the change of base. And we're going to rewrite this as y is equal to log x over log 3. Now how it works is whatever your base is always goes on the bottom. Whatever follows your log always goes up on top. Now you might be thinking, well, you just made it a lot harder. You know, it was simpler before. Well, it may look harder, but notice that these both say log now. That's base 10. I have a log button. Change of base says you can actually rewrite that even using natural log if you want. So you could rewrite it as natural log of x over natural log of 3. Because again, we have an ln button also. Now that we got in this form, we can plug in our calculator. So if I go to y equals clear, I do log x, close parentheses, divided by log 3, closing parentheses. So you just type in as you see it. And now you push graph. And that'd give you your answer. Now these graphs never just stop. It looks like it comes and hits the y-axis and stops. It doesn't. It just goes like that and then keeps going down forever. It just got so close to the y-axis it appears 1 with it. Okay, now I told you I was going to mention the by hand. I'm not going to actually graph it by hand, but I'll lead you down that path if you want to do them by hand. If I have this, remember our b to the p is equal q. This would be our b, this would be our q, and this would be our p. So our exponential form says we can rewrite it as b to the p is equal to q. So we'd have 3 to the y power is equal to x once we plugged all these in. What you do then is you create a t-chart, and it'd be best to start with the y's. So I put 0 in, 1, 2, 3. So if I put 0 in for y, I'd have 3 to the 0, which is 1. If I put 1 in for the y, I'd have 3 to the first, which is 3. If I put 2 in, I'd have 3 squared, which is 9. I'd have 3 to the third, which is 27. Now I'm out of space here. I should have cleared this off, but I'd also want to entertain putting negative values like -1, -2, -3. If I put -1 in for the y, I'd have 3 to the -1, which is equal to 1 over 3. I'd have 3 to the -2, which is equal to 1 over 3 squared, which is 1/9. And 3 to the -3 is equal to 1 over 3 to the third, which is 1 over 27. Now after you build this t-chart, then you graph it, and you'll get the same graph as what we came up with here. And that's how you would graph it using your definition of log and definition of exponential form. And that's actually the last topic there. Was there any questions on any of those?
No, thanks.
Okay. I'm going to go ahead and stop the recording.